welcome you back in geological knowledge. So in the previous lecture we have discussed about the basics of shear zone, and there we have discussed about different types of shear zone: brittle shear zone, ductile shear zone, or the brittle ductile shear zone. And there all we have also discussed about the types of shear zone, or the some shear zone rocks which are formed because different types of processes. So there we have discussed about the microbrachias, gauss, or the myelonites, cataclasites, okay, ultramyelonites, or all those things. So as we have discussed, so just revise some important factors. That is, what are the uh, protocataclysite. So if the matrix percent is between 10 to 50%, so that is known as the protocataclysite. And if the matrix percent is between 50 to 90%, that known as the cataclysite. And if the matrix percent is greater than 90%, so that is known as the ultra cataclysite. Okay. Although some recrystallization may take place during the formation of cataclasites, the dominant process of grain size reduction is by the cataclasis process. Okay, so you have to keep in mind the processes as well as the matrix percentage. Okay, 10 to 50% protocataclasite, 50 to 90% cataclasite, or greater than 90%, so that is the ultra cataclasite. And if we talk about the myelonites, so if the matrix percent is less than 50%, so that is known as protomyelonite. Okay, and if the matrix percent is between 50 to 90%, that is known as myelonite or the orthomyelonite. Okay, and if the matrix percent is less than 10%, so that is known as ultramyelonite. Okay, so in the previous video we were discussing in detail. So there we have I told you that I will discuss a very important diagram or very important figure, which will be very important for you to understand, because this is very important to you understand the processes and the uh, grain size as well as the depth range with accordance to the metamorphic grade increasing. Okay, so what is given there? So as you can see on the left side, the grain size of the fragments that have been given, and as you go from up to down, the grain size is increasing. Okay, and in the upper side, the depth range is given in kilometers, as well as the pressure temperature increasing in the right direction. Okay, and the metamorphic gradient that is also increasing. So as you can see, if we talk about fault brachia, so fault brachia, the uh, size is 5 centimeter or more than 5 centimeter. Okay, and the visible fragments, the fragments which are visible, they are more than 30% of the rock mass. Okay, and essentially the most important process behind is the incohesive. Those are the incohesive, as well as they are unmetamorphic. Okay, the metamorphic process that has not taken place in these types of brachias. Okay, and if the grain size that is less, in the range of 0.5 to 0.05 millimeter, or less than that 0.005 millimeter, the brachia is known as the fault gauze. Okay, and we have discussed that fault gauze is the very pulverized powdery material. Because of the dislocating forces, very severe, frequently the case in the thrusting process, the rocks may be grounded to a very fine clay like powdery material that is known as gauze. Okay, and if we talk about the visible fragments, so they are less than 30% of rock mass. So that was the case of the incohesive material. And you have also to keep in mind that the metamorphic gradient or the pressure temperature, that is increasing in this direction. Okay, 0 to very low to low, medium to very high. Okay, so in cohesive material, in the previous lecture we have also discussed that the cataclasites, they don't show any type of lineation or the foliation, as well as the myelonites, they show prominent type of foliations. So that's given here, random fabric or the, and in case of myeloid they are foliated. So in cohesive material, if the matrix percent is 0 to 10%, then they are known as the crust brachia or the microbrachia. And in the case of 10 to 50% of matrix, they are known as protocataclysite, as we have discussed previously. 50 to 90%, they are known as cataclysite, and more than 90, they are 90 to 100%, they are known as ultra cataclysite. Okay. And if we talk about foliated or the myelonites, so in between myelonites and cataclysite, there is quasi plastic myelonites. Okay. And if the grain size is low, grain size is very fine, very small grain size, they are known as pseudotachylite, and in the case of foliated rocks or the myelonites, they are known as superplastic myelonites. Okay. So in case of myelonites, the protomyelonite, the matrix percent is less than 5%. Okay. And the organ myelonite, the matrix percent is 10 to 50%, or the in myelonites the matrix percent is 50 to 90%, and in ultramyelonites the matrix percent is less than 10%, 0 to 10%. And in the very high grade of metamorphism, and at a very high depth of 25 kilometer, or the pressure temperature condition or the metamorphic grade very high, they are known as the blastomyelonite. Okay. They are uh, showing the pronounced grain growth in the myelonitization process. Okay. So that was the graph, and it's very important to you, for you to understand the basics, that is the grain size as well as the depth with the pressure temperature variation or the metamorphic grade variation increasing. Okay. So that was our discussion for the previous. We have promised that we will discuss this graph or this diagram. Okay. So now we will discuss about our, we will discuss after the discussion of that graph, we will discuss the recognition of the shear zone. Okay. So the narrow zones, that are narrow shear zones, that can be recognized because they show a very strain gradient from strong deformation in the center to the zone to a weakly undeformed wall rock. Okay. So what is that? So narrow shear zones, they are recognized because they show a strain gradient from strong deformation, means in the central point or in the center the deformation is strong. Okay. But as we move to the wall rock, the deformation that reduces. Okay. So weak deformation along the uh, wall rocks. Okay. So in an undeformed host rock, the strain gradient results in a characteristic pattern of increasing intensity of foliation towards the shear zone, and the bending of this foliation towards the shear zone, and the bending of the foliation into the zone. Okay. So what happens, that is the strain gradient that results in the characteristic pattern of increasing intensity in the foliation towards the shear zone, and the bending of the foliation towards the shear zone. Okay. And the pre-existing vein, that is layering and the foliation in the host rock, are displaced along such shear zones. So the most important effect that is created into the shear zone, so the pre-existing veins or the layering or the foliation planes, they in the host rock, they are displaced along these types of shear zones. So wide shear zones that is exceeding the size of the outcrops, they are more difficult to recognize. Okay. Because the shearing has been taken place to some extent that it's very important, or it's very difficult to understand or to recognize the outcrops, the size of the outcrops. And because of the high strain criteria given above, the following fabric elements, they are characteristic of the shear zone in the gneissic rocks. What are those parameters or the characteristic points? that is the an unusually regular layering of the constant thickness, and the straight linear shaped fabric in the plane of layering, and the presence of isoclinal and sheath folds in the layering with the fold axis subparallel to the lineation. Okay. Another effect, that is the presence of fabric element with the consistent monoclinic shape symmetry. Okay, so these are the parameters. Because of the high strain criteria given above, the following fabric elements they are recognized. Four types of fabric elements as we have discussed. Okay, regular layering or the straight linear shape fabric in the plane of layering, or the presence of isoclinal as well as the sheath folding as we have discussed in the previous discussion, or the presence of the fabric elements which are consistent monoclinic shape symmetry. And if we talk about the deformation in shear zone, how the deformation pattern develops. So attitude of axial surface as well as the axis of folds in shear zone, they show a wide variation in the rock types, but mostly the dominant set of fold axis is subparallel to the myelonitic lineation. Okay, the dominant set of fold axis that is subparallel to the myelonitic lineation, and that has also been suggested that the shear zone fold that is initiated with the hinge at low angle to y axis of bulk strain ellipsoid, or with the progressive deformation, they rotate to become parallel to the x axis of bulk strain, as in the diagram you can see. Okay, so this diagram you can see that initially they are at y axis, but because of the shearing they align towards the axis of x. Such idea of rotation of fold hinges through the large angles have late confirmed by recognition of strongly non-cylindrical and essentially plane folds in shear zones. Okay, so that rotation of fold hinges that have given rise to the strongly non-cylindrical and essentially plane folds in shear folds. And the most important one is the sheath fold. In extreme cases, the fold hinges that show hairpin bands, and the fold takes the form of flattened test tube, as you can see in the diagram. Okay, they have taken the shape of a flattened test tube, and when we see in the outcrops, so this essentially gives a close near circular pattern, as you would have seen in the field that the near circular pattern is formed because of the sheath folding. So these have been termed as sheath fold. Okay, when the limbs they are completely closed. Okay, circular as well as completely near circular and closed. The development of sheath folds have been explained by the uh, accentuation of initial irregularities of the bedding or the foliation surface by a strong non-coaxial deformation. Means the deformation is non-coaxial type. Okay, so that is very important to understand the process of sheath folding. Okay, as if you have gone to the field, you would have seen the formation of sheath folding. Although the folds are sometimes localized by the presence of the rigid objects like pebbles, budins, or the porphyroclasts, such rigid objects are not necessary for the development of sheath fold. Okay, so rigid objects which are the pebbles, budins, porphyroclasts, which are not affected by the shearing, so they are not supposed to be necessary for the presence of the development of the sheath fold. Since the initial irregularities they are likely to be non-cylindrical, the folds generated from them have somewhat curved hinge. Okay, because of the cylindrical folding. The initial irregularities they are likely to be non-cylindrical, so the folds generated they are the curved hinges, fold with the curved hinges. And with the progressive deformation, as the deformation proceeds, especially non-axial deformation, The hinge-like curvature are accentuated, and at large shear strain, a sheath-like structure is produced. Okay, in non-coaxial type of deformation. Now we will talk about a very important topic, that is the shear sense indicator, and it's very important for you to understand that what are the major type of shear sense indicators, okay, and how they develop. So mylonitic rocks can form in deformation histories involving bulk simple shear, coaxial or non-coaxial progression, bulk inhomogeneous shortening. Okay, so in mylonitic rocks, the there can be several types of deformation like bulk shear or the coaxial or the non-coaxial progressive bulk inhomogeneous shortening. So there are several structures both in the mesoscopic as well as the microscopic scale by which the shear sense can be determined. Okay, so we will discuss it one by one. The first and most important is the rotation of the markers. So when the walls of the myelonitized zone they can be identified, the sense of shear can be determined from the change in the orientation of the dike or the vein which enters the myelonite zone from the outside. Okay, as you can see in the diagram that is given here 21.11. Okay, the wall rock of myelonite zone that is identified, so the sense of shear can be determined by the change in the orientation of the dike. Okay, so this middle zone between these two lines, that is known as the shear zone, and the where the arrows are shown, so outer zone, that is known as the outer zone. Okay, so the shear sense, the change in the orientation of the dike or the vein that enters the myelonite zone from the outside. So within the shear zone, a dike or the vein is rotated. Okay, as you can see, the vein or the dike that is rotated uh, in accordance with the shear sense in the zone. Okay, so shear sense indicator is the rotation of the marker. By that we can identify the uh, rotation. Okay, the indication of the shear sense, or the rotation of foliation that can also take place. So rotation in the same type of shear zone, the pre-existing foliation that may rotate or the dragged to the surface near shear zone boundary, or the foliation which is developing outside the shear zone that may show bending near the shear zone walls, as you can see in the diagram, P diagram. Okay, here the same type of shear zone, the shear sense can be deduced from the sense of rotation of pre-existing foliation at the edge of the zone, as we can see. Okay, in the type of S they are rotated, okay, at the edge of the zone. Okay, but during the formulation of ductile shear zone, a foliation may continue, okay, to develop outside. So this foliation is also rotated near the edge of the shear zone, so that it makes a lower angle with the shear zone boundary. Okay, as you can see here. Okay, in the shear zone the angle is different, as well as in the outer zone the angle is different because of the formation of ductile shear zone. The foliation that can be continue to develop outside, so that foliation can also rotate near the edge of the shear zone, that will make a lower angle with the shear zone boundary. Okay, so that is the shear sense marker, as the same is given here. During the formation of ductile shear zone, a foliation may continue develop outside it. And the sigmoidal foliation, okay, across the zone at a different scale. Okay, so this represents a geometry of the xy plane of the strain ellipsoid that is produced by the simple shearing. Okay, so in the sigmoidal uh, foliation across the shear zone at different scale, so that is represented by the geometry of the xy plane of the strain ellipsoid, as you would have studied about the strain ellipsoid, stress ellipsoid, as well as the strain ellipsoid. So that is dependent onto the ellipsoid, strain ellipsoid in the xy direction. And next very important parameter, that is the SC structure. Okay, so where separate shear bands they develop within a wide zone of myelonite, the shear sense can be determined from the angle between the foliation in the shear bands and the shear lenses, or the angle between the C and S structure, as you can see in the diagram, D diagram, as you can see here. Okay, the separated bands of shear they can develop with a wide zone of myelonites. The shear sense that can be determined from the angles between the foliation in the shear band. So shear band, that is the middle one, and the outer band, that is known as the C zone lenses. Okay, the inner zone, that is shear zone, these are known as the foliation, as well as the shear lenses on the outside. So the angle between S and C, that creates the shear sense indicator. Okay, and the next another important one, that is the asymmetry of intrafolial folds, as you can see in the E diagram. when the foliation when foliation within a shear zone that is asymmetrically folded, the sense of asymmetry is symmetry to the sense of shearing, as you can see in the diagram E. What is saying, that is the foliation in the shear zone that is asymmetrically folded. The sense of asymmetry is usually in agreement with the sense of shear is the in the myelonite zone. So this sense is criteria should however be used to some caution, because the hinge of this shear zone fold are often rotated in the course of the progressive deformation. Okay, so when we take asymmetry of intrafolial folds as the marker or the shear zone marker, so there must be a caution, because the hinge of the shear zone folds, as shown by the dashed line, as you can see in the diagram E. The hinges have been shown by the dotted lines. So the hinge of these shear zone folds, they are often rotated in the course of the progressive deformation. Okay, so that is the precautionary measure to be taken. And next, another very important parameter, that is the uh, pressure shadows. Okay, so pressure shadows zones, they are the zones of protected from the large deformation because of any rigid object like garnet, feldspar crystals, or sometimes they can be pyrite, magnetite, or the quartz, or some other pyroclast. Okay, so what happens in the pyroclast? So in the deformed rocks, including myelonites or the sometimes contain large rigid crystals, they are the pressure shadows or pressure fringes. Okay, so the materials from the neighboring regions migrate to the pressure shadows zones and they crystallize there. Okay, what happens, that is in pressure shadows are wedge shaped domains which are somewhat protected from the large deformation, because they are resistant to deformation because of the presence of the neighboring rigid objects. Okay, so material from the neighboring regions that migrate to the pressure shadow zones and the crystallize there, the texture of and the grain size of being somewhat different from those of the material. Okay, and the pressure shadow zones, they are often composed basically of fibrous quartz. Okay, or they can be garnet, pyrite, magnetite, or some other rocks, some other minerals. And in the pressure with the long axis of the quartz crystal mostly parallel to the direction of the maximum incremental stretching in the matrix. Okay, the acute angle between the quartz fibers or the pressure shadow tails, and the shear direction is sympathetic to the sense of shear. Okay, there are two terms, sympathetic and antipathetic. Okay, so sympathetic means dextral movement in the right hand side or the clockwise, and antithetic in the anti-clockwise or the sinistral direction, as we will talk about later. And another very important one is the mantle structures around the pyroclast. Okay, so as you can see here, different types of mantle structures. Okay, delta type or the mm, sigma type. Okay, or the pressure ball side, as we will discuss now here. Four types of theta, uh, gamma, sorry, theta, and psi, and the sigma, as well as the delta type. Four types are there: theta, delta, phi, and the uh, delta type. Okay, so sigma and delta type pyroclasts are used as the kinematic indicators. Okay, so what happens in the process, that the rigid pyroclast or the pyroclast occurring in a ductile matrix, that tend to rotate with the when the bulk deformation is non-coaxial. Okay, so sigma and delta, they are the rigid pyroclast. They are rotated when the bulk deformation is not coaxial. The foliation in the neighboring regions, they are disturbed because of this deformation by the rotation of the blocks. So the pattern of the disturbed foliation around the rotating rigid objects may be described in general as the rolling structures. Okay. So pyroclast tail are derived through the dynamic recrystallization from the periphery of the pyroclast itself, as you can see here in the diagram. As you can see the structures or the periphery of the structures, as you can see. And the and with the increasing deformation, tail stretch out into the matrix in direction of the maximum stretching. The pyroclast decreases in the size. So when the deformation increases, the tail stretch out into the matrix in the direction of maximum stretching, as the pyroclast decrease in size. If the direction of non-coaxial, then the rigid pyroclast can rotate, and thereby a pattern of tail geometry is obtained. Okay, uh, which records the nature of the sense of rotation. What is tails of the pyroclast or the pyroclast? The surface or the bands that are distorted by the rigid objects, they may be foliated. There may be a foliation surface. So a myelonitic color bands or the myelonitic color banding, that is known as the tails of the pyroclast. Okay, and they are formed because of the fine crystallization minerals, which are derived from the dynamic recrystallization from the periphery of the pyroclast itself, as we have discussed it. Okay, so there are basically two types of geometry which are very common in the one is the sigma type, and one is the delta type. So in the delta type, the median line of the tail doesn't cross the reference line passing through the center of the pyroclast and parallel to the general trend of the foliation. Okay, as you can see here in the diagram, as the diagram is given here, that is, in case of delta type, the median line crosses the reference line. Okay, as in the diagram 21.12a, the median line that crosses the reflection line, the reference line, and in the other type designated as the uh, eta type, sorry, gamma delta type and the sigma type, sorry. The first one is delta and another one is the sigma type. The median line doesn't cross the reference line. Okay, that is the figure 21.12b. As you can see, in the first one the reference line doesn't cross. In the first one the reference lines has been crossed, but in the second one the reference line that is attached to the attached with the pyrofibroblast, as you can see in the diagram. Okay, so these are two important sigma and delta type. And in the sigma type, the median line crosses the reference line, as we have discussed. In this case the rate of rotation of pyrofibroblast is greater than that of the recrystallization. The sense of shear that can be easily determined from the sense of the rotation as revealed by the tail geometry. But for the deformation, the plane of observation must be parallel to the myelonetic lineation and the perpendicular to the foliation. Okay, for the determination of the shear sense, the plane of observation that must be parallel to the myelonetic lineation and perpendicular to the foliation. And another condition that is very favorable, that the principal axis of object, which is the axis of rotation of the pyrofibroblast. Okay, the axis of rotation of the pyrofibroblast, that is the principal axis, that is normal to the section plane. Okay, and another very important uh, shear sense indicator, that is the trails of the inclusion in pyrofibroblast. Okay, the sense of rotation of pyrofibroblast in the non-axial deformation, that can be determined from the relative relation between the trails of inclusion, that is SI, and the foliation outside, SE. Means the trails of inclusion that is known as SI, and the foliation they outside, they are known as the SE. Okay, and this criteria can be well determined, that can be used to determine the sense of shearing only if the SI and the outer myelonetic foliation are produced of a single ongoing deformation. So this is important condition for the determination of the shear sense, that this criteria can be used only if deformation, to use the determine the shear sense, the sense of shear only if the SI and the outer myelonetic foliation, that is SE, they produce of a single ongoing deformation. Okay, the pyrofibroblast that may have grown into earlier phase of deformation. Further, ductile shearing rotate its discordance with the create discordance is created between SI and the SE. Okay, so what happens, that is the ductile shearing that rotate its, and discordance is created between the SI and SE. And the paracrystalline rotation that may produce S and jet type of patterns of SI in pyrofibroblast. S pattern indicates anti-clockwise rotation, left-handed shear, and jet pattern that indicates clockwise rotation, right hand shear. Okay, as you can see here in the diagram. Okay, in the diagram C and D, the C type, that is S type structure, and that rotates the anti-clockwise. Okay, and in D type, in D diagram, that is the Z type rotation, that is the clockwise rotation. Okay, and another very important parameter, that is mica phase. Okay, so what happens in mica phase, that is the myelonites Sometimes they contain asymmetric lens shaped coarse grains of mica that is oriented oblique to the dominant foliation. Okay, so the mica grains, they are uh, oblique in nature. Okay, oriented obliquely in the mica grains. 1 minute. To the dominant foliation, and these have been described as mica fish. Okay, sometimes a number of mica fish are joined by fine trails of mica. The acute angle between the mica fish and the foliation points towards the direction of shear. The sense of shear that can be determined from the asymmetry of the mica fish. As you can see in the diagram here, sorry, here in the diagram F. Okay, the sense of shear can be also determined from the asymmetry of the mica phase. And what happens during these have been described as mica phase, the flakes of mica that are oblique to the dominant foliation. The acute angle between the mica phase and the foliation points towards the direction of shear, as you can see in the F diagram. That is the acute angle between the mica phase and the foliation that points towards the direction of shear, and towards each end the tip of mica phase bends towards the direction of shearing. So that is very important phenomena or very important clue for the determination of shear sense indication. That is the towards the end, as you can see where the arrow is given. At the top one the arrow is there, and then bottom one the arrow is opposite direction. The tip of the mica phase bends towards the direction of shear movement. So that is very important clue for the determination of shear sense. And if we talk about another important parameter, that is the asymmetry of quartz crystal, that is axis preferred orientation, c axis as preferred orientation. Okay, and the oblique foliation in dynamically recrystallized quartz aggregates, they have also been used for the shear sense indication. And another very important parameter, that is the slip on grain scale faults. Okay, the slip on grain scale faults, that is also very shear sense of slip and the rotation of grains. So the mega crest of some minerals such as feldspar in malonites or quartz, they show brittle behavior and undergo micro faulting. Okay, so because of this, the oblique fault segments, they slip past over one another as well as rotated during the non-coaxial deformation. Okay, so the slip may be either antithetic or sympathetic, as we have discussed that antithetic or sympathetic. Okay, anti if they are antithetic means they are in anti-clockwise direction, but if they are sympathetic they are dextral or the clockwise direction or right hand direction. Okay, so slip may be antithetic or sympathetic with the respect to the sense of shear in the shear zone. For example, dextral slip of microfaults in a zone of dextral shearing, that is sympathetic. And if the fault are initially oriented at low angle to the foliation, the slip of them is generally sympathetic, and they are at high angle, the slip is antithetic. Okay, thus the sense of slip and the rotation of micro scale faults that can be used to determine the sense of shear, as you can see in the diagram. Okay, in the diagram A, the microfractures or the microfaults, they are oriented at low angles to the foliation plane. The slip of them will be sympathetic, as in the diagram A you can see, because they are moving clockwise direction. Okay, and dextrally means right hand direction. And such low angle microfaults in grain scale, they can be safely used to determine the sense of shearing in the matrix. And although rotation of the microfaults, that may be either sympathetic, as in the case of A diagram, or antipathetic in the B diagram. Okay, it's very important for you to understand the empathetic and the sympathetic, means dextral or sinistral, or right hand movement or the uh, left hand movement. If the movement is dextral, that is right hand movement or the sympathetic, and if the movement is left hand, that is uh, antithetic or the sinistral movement. And there is in the C type that is given here, the if the microfaults were initially at a high angle to the foliation, the slip of them is antithetic. As you can see in the diagram, see that high angle, angle is very high, but in case of A and B, angle is not very high. Okay, so in case of C diagram, the high angle of the foliation, the slip of them is antithetic, and this type of slip is somewhat described as book self sliding or the domino effect, when the acute angle between the foliation and the slip plane is reduced by their rotation in the direction of the shear. As you can see, it looks like that the books are kept in a self. Okay, that is shown. They are sometimes described as the book self sliding of the domino or the domino effect basically. So the shear sense in the matrix, they may be deduced from the such book self sliding, that in which direction they are sliding towards each other, as you can see in the diagram. Okay, the and the same is given here. Okay, as we were discussing, the fault, the oblique faulted segment slip past one another as well as rotate during the non-coaxial deformation. The slip may be either antithetic or sympathetic with the respect to the sense of shear in the shear zone. For example, dextral slip on the microfaults in shear zone or the dextral shearing in sympathetic, and the same is given here, that is we have discussed. Okay, so sense of shear, that is the slip of rotation of micro scale faults that can be used to determine the sense of shearing. Okay, so that was our important and very important discussion of this sense of shear, that how the shear sense indicators are used. Okay, thank you. And the PDF of this both, that is part 1 and part 2, that you can get from the Telegram channel. Okay, thank you.